Then, so we finished the blog with Radim Panis from Silesian University in Opava, who's going to talk about deterministic aspect of the gamma ray variability in blazars. So, Radim, you have 25 minutes. You could please share the screen
Thank
now.
you, Camille. Thank you, Camille.
Yeah, sure.
Do you see my screen?
Not yet. Let me see. Okay, now we can see it now.
You see the presentation, yeah?
Yes, okay, we have it now. Thank you.
Perfect. I will start because I think we moved somehow in the timetable. So my presentation is about the recent work we have done with my collaborators and colleagues Gopal Bhatta and Zdeněk Stuchlík. And this work is regarding the recent paper we have published, not published, we just submitted last week or 2 weeks ago into APG. And I will try to briefly put together the main ideas of this paper in some 20 slides. So this presentation contains these sections, which is motivation. Then we will speak some little bit about the data. Then we will put some effort in order to explain some technical details about the analysis methods and its whole algorithms. In the end, I plan to discuss some astrophysical conclusions and pretty much the all. In the graphics, we can see the Fermilab satellite, which actually the data is coming from. Of course, this is some not real picture, but some interpretation by some graphical engineers. So again, to the motivation. So in the very beginning, so we have some observation data, and we will try to characterize the general features of the supermassive black hole systems. And these data are actually coming from 20 blazar sources, which I will shortly present in next slides. They are in the gamma ray, and the gamma ray light cubes can provide insights into innermost regions of black hole systems. Even in astronometry, the gamma ray is also quite, let's say, newer feature in compared to another wavebands. We try to use novel nonlinear analysis methods in order to squeeze the most information from this data. And this gamma ray variability of blazars are found to be very represented by flicker noise. So we try to adjust the methods in order to take this in account. We try to describe all those analyses made in nonlinear fashion. So we try to describe the deterministic and stochastic nature of the observed gamma ray variability and possibly connect the results to the implications of strong disject connections and try to fit it to some well-known models. And as already mentioned, we use somehow novel approach of frequency quantification analysis, which provides more accurate measures of determinism, predictability, and entropy. And in addition, we estimate the timescales of these 20 blazars. Well, we can briefly look again to the data. So the data are coming, as already said, from Fermi Gamma Ray Space Telescope launched by NASA in 2008. And in the energy band extending from 10 mega electrovolts till 100 giga electrovolts is the operational radius. And our data there are more instruments in these satellites. Our data are coming from LIT, and which detects individual gamma ray sources. I think, and I hope it's not necessary to actually say what the blazars X-ray are, but we can describe them as extragalactic supermassive black holes, and In contrast with quasars, the relativist jet is closely pointed towards the Earth, and there are some more distinguishing and dividing between the blazars, but we mostly studied the properties of the dividing according to power spectral density, which divides blazars into flat spectral radio quasars and BL-Lacrate sources, which will be described in next slide. And the general model, which is already and also very well known in the community, is that jets are coming from some interplay of magnetic field, fast rotating black hole, and supermassive black holes actually, and plasma, of course. And yeah, so let's look on the data again on the sources. So the sources are depicted in the legend, divided into by red and blue colors into BL-Lux and flat spectral quasars, while BL-Lux are again less powerful, and the cyclotron peak lies in the optical or X-ray region, while by flat spectral blazars, cyclotron peak lies in the lower frequency. So I will again stress how this is divided by power spectral density, behind which is linear statistics and Fourier transformation. And one feature of the data, so they are collected within 10 years with 7-day spinning. So doing simple math, one should obtain around 513 points in time series. But common features, astronomical data, they have missing observations, and so so-called gaps. So our average of our data set is 430. Which is the feature of uneven sampling in the data. Let's look again on some advantages or some common features of linear analysis. So this most used statistics, or I mean most used method in astronomical data, is very powerful tool, but it's limited to the second order moments. And as also some authors states, it fails to incorporate the information about the inherent nonlinearity and non-stationarity, which actually one should agree that nature is not behaving very linearly in its nature. So again, but I will present some basic features about nonlinear analysis. Well, it can be described as apparatus which can probe into dynamical states of deterministic systems, and which provides a framework to the inverse problem, which we could somehow say the greatest goal of nonlinear analysis will be the restoring of equation of motion of the underlying system. However, it's not so easy as it looks maybe. And this whole thing is based on mathematical theorems from the 80s, and I once can say from the 70s as well. And these taken theorems from 80s simplifiedly says it reflects, one can reflect the dynamics of the whole system observing only one variable or one degree of freedom, which is a very, very good feature when we have when from astronomy we have just one-dimensional time series. These whole things are approached by many numerical approaches, the methods like fractal dimension and Lyapunov exponents, and I will say these things are, as handling practical things and data, they are still under development. And theorems are considering infinite amount of data, which is quite luxurious demand, doing something practically. So the important feature of putting the relationship between how much data one needs in order to do some statistics is expressed, for example, by Smith. But to find some analytical relationships is, I would state, is quite impossible, because the features the data can have is quite large. And from the practical point of view, I can stress out the two things. The when one has data with gaps, so one can interpolate the data, but then it adds some artificial dynamics. So if you add some more than half the points to your data sets, you can really like consider if this has any sense. And for sure, when doing any kind of data which coming from some sensors, one can consider also how much noise it can have and errors and such things. Very nice article about all this problemacy, and is Bradley and Kant's. I should just recommend to check it. Next, I can say in order to further explore the nature of gamma ray variability on the sample blazars, we have adopted a number of approaches to the chaos study. So we consider many available algorithms and libraries, and we try to choose the most efficient for our situation and our data. The emphasis was given to use algorithms with small amount of inputs, where the less parameters, the easier is the physical interpretability. So I will somehow connect to last speech, where using machine learning sometimes provides very accurate fits for some kind of tasks, but sometimes to use somehow less sophisticated methods can also provide many advantages. And this statement comes somehow in hand with creation of physical theories, where the less things you put into the theory, the more probably you create some theory actually. And the algorithms handling nonlinear phenomena are also sensitive to the inputs. When one tries to do something, one can clearly feel this feature, while chaotic data are very sensitive to the initial conditions known feature. But I would say also the algorithms are also very sensitive to the input. So when one uses the small amount of inputs, one can also, within computational resources, also investigate the interplay between parameters and their combinations. So this exactly we have done, and we have some for our main algorithm for whole analysis is the recurrence quantification analysis, which will be presented in next slides. And I will say the main parameters which we studied and which we try to find the best combination of this input to obtain non-unbiased results are time delay, embedding dimension, and L minima and maximum recurrence rate versus average. Yeah, these things are not introduced yet, but I just want to stress out we explore the combination and use extensive testing in order to find the best inputs. So our whole testing and searching for best inputs and combination of them has one strong assumption of, and namely we created artificial light cubes which mimic the real data. And these artificial light cubes are produced with a package ROBER published in library in R, and the papers published in Journal of Statistical Software. And especially function TSGN we used has 15 parameters of producing light cubes. And in order to fit it to our situation, so we set up most of the length, introduce gaps, and we assumed higher noise content. The rest of the parameters has to be also randomized in order to avoid any our choosing which will be affected by our choices. So we use some pseudo-random numbers. We can check how these artificial light cubes look like. In the first picture, this light cube where we can observe in red points the gaps which have been introduced, and they are filled now with red points, and by interpolation, the same one can observe in the real data, and the sources are, or the names of the sources are also depicted. So as one can observe, some of these light cubes obtain some quite significant amount of gaps. And in order to produce most unbiased result, we analyzed both situations if we fill the gaps with interpolation, so as if we don't. And the result was somehow quite nice because the feature was coming out as the same. Now this is a quite important slide, which I now feel quite sorry to not to make more extensive. According to the speech of Mark Abramovich, he was several times stating how important is topology when doing any science. Because this slide is quite saying something very similar. When doing any nonlinear analysis, one should map the one-dimensional input to the more dimensions in order to fit or mimic the underlying system in topological sense. And this is done by embedding, where embedding is how it constructed is in the phase equation. And here we can see the original time series YT is mapped into more dimension, and the number of dimensions is M, and there's also another parameter tau. And these things help to, from one-dimensional input, construct something which resembles the same thing in phase space, because dynamical systems and even everywhere in physics, every system described by the equation one can map into phase space, which is saying basically all the properties of the system. And mathematical theorems taken saying somehow just this is possible from one-dimensional input. Yeah, but one should say like fulfilling many assumptions. But from the practical point of view, one need to use algorithms and some numerics, and we used average mutual information and LKR algorithm, which paper is named Practical Method for Determining the Minimum Embedding Dimension of Scalar Time Series, which is from 97 and is cited just 1,738 times, which is actually was to me kind of surprising how much is this thing not used when doing analysis, because it's very proficient. And all these algorithms are, all these two algorithms are just made in order to construct the embedding, which is the input for our main algorithm, recurrence quantification analysis. And yeah, we have not much time in order to describe all these details, but this is the tool made after the recurrence plot, which has been made in '87 by Ekman, and it's just graphical tool depicted here in order to study recurrences of some dynamic system. And I would say people were just lazy and they didn't want to look to the graphics, so they constructed the numeric quantificators of describing the whole thing. And these things are just describing the black dots, or even doesn't matter what color dots in these graphics. And the physical interpretation or time series analysis interpretation is there, reflects some properties as how much deterministic the system is, or how much predictable the system is, or entropy, how much information does the data contain. And this whole thing is old, I don't know, maybe 30 years, but it's in time series analysis already widely used, but there's something which is still not very clear. There's kind of uncertainty of setting up this epsilon parameter where constructing the whole recurrence plot. And we try to somehow find a solution of what is the correct way of setting up epsilon, because many authors do is just they say some value of epsilon is correct and then use it, which kind of not very scientific, I would say. So we made the recurrence quantification analysis as a function of the epsilon, which is then input for the recurrence rate measure. And the recurrence rate just says how many points you can see in the whole graphics. And then out of this, every of these graphics then hold another recurrence quantification analysis measures are derived. And when we use this, we made this for many recurrence rates, and then we averaged the result in order to have more accurate measure, because we didn't want to choose one epsilon and say this is the correct thing. And how we set up the whole parameters and epsilons is explained here in the next slide. Yeah, how we approach the problem. So we created many tables, like here in the left, where there are columns like CNR, which is signal to noise ratio, which actually signals to noise ratio was one parameter when constructing artificial light cubes. So we define some range of artificial light signal to noise ratio when generating the light cubes from 5 till 001. And then all the other parameters have been randomized, and then we check the ability of some settings of our recurrence analysis has done the job of sorting them according to the signal strength. And this is expressed by MD, like determinism measure, which M states for average, like mean determinism measure. And all this table is sorted according to this mean determinism, when we can observe that this particle settings says like 3:1 signal to noise ratio is the most deterministic, then comes 5, then comes 0.5, and so and so. And here is expressed the length of the time series, and these already discussed tau and M things, and these are another average measures. Well, I need to stress now like 300 or till 500 data points for this kind of analysis, not much. That was actually one thing made us to think about more tricky ways how to squeeze the most information from the data. And I would say this is, even if it's not sorted perfectly, this is very, very nice result. And how efficiently some configuration works is expressed in the table on the right, where we consider these four things: RR, L-min, embedding, and tau. And we stressed, we checked, or we explored all the combinations between the settings, where L-min hashtag goes from 1 to 10, embedding from 1 to 3, and tau to 1 to 3. And these things are not saying what was the exact value of the embedding, but is the approach, how it was set up, because we considered all the data as a set, not as individual sources sometimes. So when we put embedding, for example, hashtag 2, it was the mean of all the embeddings calculated by LKL methods. Hashtag 3 was the maximal, and 1 was the individual value. So this was one natural assumption that some basic statistic can express and provide more accurate results when putting them as input for recurrence quantification analysis. RR is simple, the highest value where we were averaging to. So and measure 1 and measure 2 are the measures of the quality of the sorting, which is really not enough time to express how it was done. And I would say this whole thing took something like 100 hours of my laptop. However, with saving of results, and I mean, not final results, I mean the in-between calculations, in order to check how it was proceeding. Yeah, now we can see how this whole thing worked on the real data, because this whole thing was just used in order to find certain parameters for our real situation. And this is the application R20 blazars, where we can see some clear pattern where the red ones, which are flat spectral blazars, are kind of separated from the blue ones. Yes, one can say, yeah, the first is blue, but from the point of technical issues, 208 points, which has been used from this blazar, and this has just half of the data, or the rest is the gaps. So it could be clearly said this is not suitable for any kind of analysis. The rest, the same, the AO blazar has the second least amount of data, and the TON has also the third least amount of data. So somehow we can see the separation is very nice. Here one can observe as well the average measures, which are depicted in next slide graphically. And these and other things which are providing also some information about the whole thing are actually scoring measures, and we have not enough time to describe them. Like graphically, we can see that the patterns are also visible, where the deterministic content is also visible, that flat spectra have more determinism. Entropy just says how much information they contain, so flat spectra blazars contain also more information than BLX. So and mean L is some measure of predictability, where one can see that predictability of flat spectra blazar is smaller than BLX, and this could be explained by the feature of the feature that complex nonlinear systems. Yeah.
You already have 25 minutes.
So how much time do I have now?
None.
None.
It's been already 25 minutes.
Okay, you could say faster.
Yeah, no, it's okay. You just you know.
Okay, I will quickly come to the astrophysical conclusions as this last part actually. So the astrophysical interpretation can be that flat spectral blazars are likely dominated, and therefore the jets possibly are less magnetized and consequently provide less favorable conditions to stochastic processes. And the result that the dominant physical processes in flat spectral blazars are more deterministic nature can be interpreted in widely accepted scenario that jets are powered through the extraction of rotational energy of the supermassive Kerr black hole. Here, well, it is quite interesting connection to the work of the authors led by Tavecchio, which is highly cited author in this field. And these guys just fit the data with stochastic equations and differential equations, where this is particularly Kolmogorov equation, and it just has the as deterministic and stochastic part, and this perfectly fits our results actually, where this blazar 3C453.3 is by our analysis denotes as the most deterministic, and here it obtains the least stochastic term value. And yeah, so pretty much, and then they are in orders of 15 weeks, and I will rather not speak about the details, we have not much time. And yeah, so to conclude the work, so we have analyzed the linear properties of 20 blazar. We used a novel approach of RQA. The optimal inputs of our algorithm have been extensively tested, and the pattern of distinguishing the group of blazar is visible also in our analysis. So thank you for your attention, and if there's any questions, I would like to answer them.
Okay, thank you very much, Radim, for your talk. So any question? Yes, there is one question here by Agnieszka. So go ahead.
Hello. So nice talk. Thank you for this presentation. I just want to first comment and also maybe inform that we worked actually with this method of the recurrence analysis with respect to the X-ray data from accreting black holes, and Petra Sukova is an expert of this.
Yeah, we cited your paper actually.
Yeah, so I didn't know about this. I just wanted to say because she's at this conference as well, so maybe she could have more question about this. I remember that we also use such a technique as this correlation dimension, and the significance we defined was based on this Renyi parameter. Yes, so this is probably similar numerical scheme that you have. Well, my question is just simple about the underlying physics, yes, because you had only very fast conclusions about the underlying mechanism for this nonlinear variability. What is going on? This is emission from jets, right?
Yeah. So we studied the timing signal from these 20 blazars from the NASA database available. And yeah, so physical conclusions are we just assume we have the astrophysical conclusion are just assuming, and somehow also saying the same. We actually somehow prove the same things, like for spectral blazar, I somehow is dominated and BLX have been found to have abundant with streaming particles that can contribute to the enhance stochasticity. And honestly, I made this presentation more technical in order to fit the session, while also even this way I haven't enough time to express all the things. And to your analysis, yeah, this was one of the the works you made. I am totally aware of the things you made, and it was kind of motivating us to somehow do it better, and not only say we should average till 10% or something, but we provided some framework how to make it to more scientific and say where to average is the correct approach, yeah, because this hasn't been answered in many authors, and this kind of question is omitted all the time. So we try to provide framework in order to find correct epsilons, yeah.
Yeah, so I see here that you are referring to the deterministic nature of the magnetically arrested accretion, for instance, yes, and the cyclic nature of this magnetical arrestment. This is what you mean here, yes, in your comments.
Yes. This is widely accepted scenario about the origin of the whole jets. Actually.
Thank you for the answer.
Thank you as well.
Thank you. There are any other questions from the participants so far? Okay, so I think that's all. So thank you very much, Ryan, again for your talk.